Hello, my name is Matthew Tannehill. I'm a senior at FSU and I'm enrolled in the Computer Science Bachelor Degree program. I'm one term away from graduating. I just have to take French 3 over summer and then I'm done. I'm very excited about that. But this is my presentation for CIS4930, Top 10 Algorithms. I'm going to be introducing you to the naive Bayes classifier algorithm. The naive Bayes classifier is based on Bayes' theorem. From this relationship, it inherits from Bayes' theorem a way of calculating the posterior probability. That's the probability of y given x from the probability of y, the probability of x, and the probability of x given y. What this translates into is an algorithm that is good to use in solving certain types of problems. Some of these problems these algorithms excel at efficiently solving include categorizing spam, medical diagnosis, and OCR document reading, to name some of the more popular ones. I am mostly interested in naive Bayes classifiers and their use in machine learning. One of the hottest topics in computer science today is machine learning. While I have found many different definitions for the term machine learning, for our purposes, machine learning can be described as predictive modeling of pattern recognition. Machine learning revolves around developing self-learning computer algorithms that function by virtue of discovering patterns in a data and making intelligent decisions based on such patterns. This is where the naive Bayes can be used to help. In machine learning, naive Bayes classifiers are a family of simple probabilistic classifiers based on applying Bayes' theorem with a strong naive independent assumptions between the features. In machine learning, you must be able to accurately make predictions about a particular data model given a finite sample data set from the model. I think when using machine intelligence, operating on a model of its environment, naive Bayes classification can make predictions about the model efficiently. Naive Bayes can make these predictions by classifying the model's data into most likely classes. A machine can display a level of intelligence by acting on the most likely predictions. Not only is Bayes extremely good at what it does, it's also extremely easy to learn and very easy to use. And it can be scaled up to large data sets very easily. This is what makes it so popular. Let's see how this all works. The naive Bayes operates with a special characteristic making it unique. It assumes that the effect of the value of a predictor x on a given class C is independent of the values of other predictors. This assumption is called class conditional independence. In a regular Bayes classifier, each predictor is calculated with one predictor dependent on another. As the number of predictors increase, it also exponentially produces too many calculations due to the increased dependencies across the predictors. Let's look at Bayes' theorem. There's going to be four major components to it: the probability of the likelihood, the probability of the class prior, the probability of the predictor prior, and the probability of the posterior. On the right-hand side of the equation, we have the probability of the likelihood of an event, that's x given c, multiplied by the probability of the class prior, and then you take that all and divide it by the probability of the predictor prior. If you do this, you'll come up with the probability of the posterior. But since in naive Bayes, we are dealing with class conditional independence, we are mainly concerned with the probability of the likelihood multiplying by the probability of the class prior. Let's look at an example of the naive Bayes classifier in action. This is a doctor who diagnoses patients on whether or not they have the flu. He's had several patients come in to see him so far today, and he's kept track of their symptoms. And then he's also kept track of whether or not later on they found out if they had the flu. He's used this data as test data to populate for the naive Bayes, and now he has his next patient come in. We'll call them patient X. Patient X says he does have chills, he does not have a runny nose, he has a mild headache, and he does have a fever. We're going to use the naive Bayes and the test data to figure out if this patient has the flu or not. Now, the first step you have to do is calculate the individual probabilities for each of the predictors. For example, if you have the chills and you have the flu, or you don't have the chills and you have the flu, and so forth and so forth. This is part of the independent nature of naive Bayes. Then once you have the individual probability for each one of the predictors, then all you have to do is multiply together each one of the features that are relevant to your problem, and it looks like flu2 has a 0.0185% of being most likely, so it looks like the patient X does not have the flu. One of the problems that can result from having each predictor independently calculated is that the probability of any X given Y can result in 0. Even if you have a very high probability for every other value in calculating the probability of X to the n given Y, when you multiply by 0, it will produce a 0 value overall, thus giving substantial evidence of a most likely case that the data will be misclassified. This is referred to as overfitting. There are several different ways to fix this problem, but I will give the strategy for one in particular. To eliminate a 0 result, you can create fake data accounting for every possible scenario to happen at least once. Then, no matter what data is targeted, an accurate representation of the predictor's probability is given and the case is accurately represented. The only thing you need to be careful of is not to add so much fake data so that it decreases the accuracy of the test data used to create the probabilities. Let's talk for just a little bit about machine learning, which the naive Bayes is so useful in. First, let's see, how do humans learn? Humans learn through experience, through seeing, touching, feeling, hearing, just basically experiencing the world. Through this, we create our own test data set. From that test data set, we are able to make predictions about our environment. When you can make predictions about your environment, you're displaying a level of intelligence. When trying to figure out how to get this all done, the machine learning, we look at the human brain. The problem is the human brain is very complex. It is quite literally the most complex biological machine man has ever come across. I wish I had more time to talk about this next topic, but I'd like to talk about a company called Numenta. It's out west, and it's got a couple of guys out there. It's a startup, and they're working on machine learning right now. Now, what they're doing with machine learning isn't what artificial intelligence is doing, where they're just trying to create a brand new machine intelligence. And it's not what the other guys are doing with the trying to duplicate the brain precisely by creating hardware to duplicate the neurological mapping. What they're doing is they're looking at the way that the brain processes data. And then once they figure out how the brain is processing the data that's coming into it, they're just trying to duplicate what functions the brain does afterwards. One of the most interesting functions of the human brain is that no matter what kind of data the brain receives, whether it's from your eyes, your mouth, your ears, your touch, to the brain, it's all identical. It doesn't distinguish from one to the other. Once the brain starts storing this data as experiences, it creates a test data set itself. And from this test data set, it starts making predictions about the world around it. For example, I'll bet you can predict what word I'm going to use at the end of my, see, now I never said the word sentence there, but I'll bet your brain had already predicted that's what I was going to say. So it had already put it in your head. Now at Numenta, they're using current technology with data structures and algorithms like the naive Bayes to duplicate the functionality of the human brain. It's going to be really exciting to see where they're at in a few years with machine learning. Naive Bayes classifiers can help solve certain problems with machine learning despite their naive design and simplified assumptions. With a small amount of training data, they can accurately estimate the parameters needed for most likely predictions on classifications of data. As data grows in the number of features, the independent nature of the naive Bayes allows it to grow linearly, unlike its counterparts in classification that grow exponentially. As the machine learns about its environment through sensors and other data, a model will be constructed. It will be far too much data to process, if every aspect of every piece of data is implemented in a calculation for the interaction with the environment. Naive Bayes makes an assumption of each feature's independence on the data it processes, which simplifies the processing and still gives an accurate means to classify the data. Once properly classified, the data is used to make a most likely prediction on the environment model that will give the machine a type of machine intelligence. As a machine gains more data about its model, the naive Bayes classifier becomes better at helping the machine make better predictions, and thus you have a learning machine.